All right, so here's the thing about black holes. For the longest time, and I mean for decades, scientists treated them like they were pure science fiction. Just these bizarre mathematical solutions that popped out of Einstein's equations. And get this, Einstein himself didn't think nature would actually allow these things to exist. He thought the universe had better sense than that.
No, no, no. This can't be right.
No, absolutely not.
Still no?
No.
No.
I'm afraid the answer is no.
But here's where it gets wild. We were wrong.
Okay, so the Einstein field equation says the universe bends space-time in proportion to energy. But this fraction, where did all these g's and pi's even come from? And how does it turn into a whole swirling black hole?
Okay, stop. They're real. And they're not just real, they're out there right now, actively shaping the fate of entire galaxies. So what are we actually talking about here? Picture invisible regions of space that seem to break every rule of physics we've ever written down. They devour matter. They bend light around themselves like it's nothing. And some of them, they shoot out these absolutely massive jets of energy that blast across entire galaxies. It's insane. But here's what really keeps scientists up at night. The more we learn about black holes, the more questions we have. We're talking about everything, from how dying stars collapse into these cosmic monsters, to Hawking radiation, which, by the way, is its own mind-bending rabbit hole, to the quiet little black holes hiding in our cosmic neighborhood, all the way up to the supermassive behemoths at the centers of galaxies that have billions of times the mass of our sun. So how did we get here? How did black holes go from being weird math curiosities that we scribbled on chalkboards to being the main characters of modern astronomy? Where do they come from? How can we even detect something that's literally invisible?
Nothing here. Whoa!
Hi there.
You're what I was looking for.
Found me.
Nice to meet you.
Likewise.
And just how much power do these cosmic abysses actually have over our universe? But before we answer any of that, we need to go back to the beginning of the story. Okay, so the story of black holes, it starts in the most unlikely way possible. Albert Einstein releases his theory of general relativity and completely rewrites how we understand gravity. Game changer, right? But then, almost immediately, a physicist named Karl Schwarzschild takes Einstein's equations and finds a mathematical solution that predicts something absolutely bizarre. Regions of space where gravity would be so extreme that nothing could escape, not even light. Sounds like science fiction, doesn't it? And honestly, that's exactly how people treated it back then. Nobody took it seriously. Not even Einstein himself believed nature would allow something that radical to exist. For most scientists, black holes were just mathematical curiosities. You know, ideas that look pretty on paper but never actually show up in the real world. They had no idea what was coming. Things started to shift in the late 1960s when astronomers discovered something new: neutron stars. Picture this, an entire star crushed down into a sphere just a few kilometers across, so dense that a single teaspoon of this stuff would weigh billions of tons. In 1967, they detected the first pulsars, neutron stars that spin and shoot out beams of radiation like cosmic lighthouses. And that's when scientists started thinking, if nature can create something that extreme, why not go one step further? And that's when 1971 happened. Enter Cygnus X-1. This mysterious X-ray source had actually been spotted by rockets 7 years earlier. But it wasn't until now that we figured out what it really was. Cygnus X-1 was part of a binary system, 2 stars orbiting around a common center, like partners in a cosmic dance. Except there was a problem. Only one star was visible. The other one? it had seemingly vanished. Astronomers realized the visible star was orbiting around something incredibly massive, but completely invisible. The conclusion? It had to be a black hole. And this wasn't some shy, quiet companion either. This black hole was literally stealing matter from its partner star. When that gas fell toward the abyss, it heated up so much, it released X-rays, like a cosmic scream, saying, "Hey, I exist." It was the first major evidence that black holes weren't just theory, they were real galactic neighbors. Over time, the evidence just kept piling up. At the center of the Milky Way, for example, scientists tracked stars spinning around like tops, orbiting an invisible point. There was no doubt. Hidden right there was Sagittarius A star, a supermassive black hole with millions of times the mass of the Sun. This discovery was so groundbreaking, it won the Nobel Prize in Physics in 2020. Cementing black holes as central characters in our universe, not just theoretical side notes. Today, we know black holes come in different sizes and are scattered throughout almost every galaxy. What started as an improbable idea became one of the most fascinating discoveries in modern science. But that brings us to an even more intriguing question. What exactly are black holes, and how do we study them if they're literally hiding from our view? All right, so black holes can be born in different ways, but the most famous one, it's basically the explosive finale of a giant star's life. When a star that's at least 8 to 10 times the mass of our sun burns through all its fuel, it can't hold up its own weight anymore. And what happens? A dramatic collapse, followed by a spectacular supernova. What's left in the center is an object so compact that not even light can escape it, a stellar black hole. But here's where it gets interesting. There's also a cosmic shortcut, direct collapse. Without needing to form a star first, this process can create massive black holes right at the beginning of the universe, like true cosmic seeds that over time fattened up until they became the supermassive black holes we see today at the centers of galaxies. And as if that wasn't enough, there are also the mysterious intermediate mass black holes. Not small, like stellar ones, not giants, like supermassive ones. They're somewhere in between, with 100 to 10,000 solar masses. They're rare and hard to detect, but we suspect some are hiding in star clusters, like in the case of 47 Tucanae. It's like they're the teenagers of the black hole family. We know they exist, but we still don't really understand how they behave. So if black holes don't emit light, how on earth do scientists find them? The answer? By spying on what's happening around them. One classic method is observing the accretion disk. When a black hole steals matter from a companion star, that material spins around it at absurd speeds, heats up to millions of degrees, and emits X-ray radiation. It's almost like the black hole is lighting up a neon sign that says, "I'm devouring something over here." Another trick, analyzing the movement of nearby stars. That's how we discovered the supermassive black hole at the center of the Milky Way. Multiple stars were orbiting an invisible point, like bees circling around a phantom hive. The only plausible explanation? There was a black hole with millions of solar masses hiding there, dictating the entire stellar choreography. In recent years, scientists gained a brand new sense for hunting black holes: gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, and the Virgo Observatory detected for the first time the ripples in spacetime produced by two black holes colliding. It was like hearing the universe playing a cosmic bass drum, and confirmation that we were on the right track. And it doesn't stop there. The gravity of a black hole is so intense, it can bend light from more distant objects, creating what's called gravitational lensing. Thanks to this trick, we've managed to catch black holes that had no companion star and no accretion disk. In other words, the true cosmic ninjas. All right, now we get to the fun part, the superpowers of black holes. One of the most famous is something called spaghettification. Get too close to a black hole, and the difference in gravity between what's nearest to the event horizon and what's farthest away is so extreme that your body would be stretched out like a strand of spaghetti. First your feet, then your torso, then your arms, until you literally become cosmic pasta. Another curious detail, all black holes spin. And some of them spin like they're trying to win a cosmic Formula One race. The black hole GRS 1915 plus 105, for example, spins more than 1,000 times per second. And it doesn't stop there. Black holes can launch jets of particles at speeds close to the speed of light. It's like they're natural particle accelerators, but on an astronomical scale. These jets can cross entire galaxies, influencing the formation of new stars. In other words, they don't just destroy, they also help build. And let's bust a myth real quick. If the sun were replaced by a black hole of the same mass, nothing would be sucked in. The planets would continue in their orbits like nothing happened. The only difference is we'd lose the sun's light and heat, meaning the solar system would turn into a giant freezer. No cosmic vacuum cleaners here. Black holes only cause trouble up close.
Even with all these discoveries, black holes still hold secrets that feel almost like they're taunting us. One of them is the famous Hawking radiation. Stephen Hawking showed that, theoretically, black holes can emit particles and lose mass over trillions upon trillions of years. In other words, they would slowly evaporate. It's so slow that even if you waited for the entire universe to age, there'd still be time left on the countdown. Another common confusion, heavily fed by science fiction movies, is thinking that black holes and wormholes are the same thing. In the movies, they become portals to other universes. In science, we know it doesn't work that way. Wormholes are theoretical shortcuts through space-time, while black holes are dead ends. Once you're inside, there's no way back. And of course, there are always the extreme examples that give you a sense of scale for this phenomenon. Gaia BH1, for instance, is the closest black hole to Earth, at only 1,500 light-years away. Meanwhile, the Colossus TON 618 is the most massive one ever identified, with an absurd 66 billion times the mass of the Sun. Between the quiet neighbor and the mind-boggling giant, black holes show us they can be as varied as they are impressive. Looking back at the history of black holes is almost like flipping through a cosmic photo album of discoveries. We started with equations that seemed like mathematical daydreams, went through decades of skepticism, and arrived at a point where we can actually photograph the shadow of a black hole. It's like going from chalk drawings on a blackboard to capturing real images with telescopes scattered across the entire planet. But black holes aren't just historical milestones. They're central pieces in the architecture of the universe. Today, we know that practically every galaxy has a supermassive black hole at its center. And they're not just sitting there like cosmic decorations. Their gravity and energy jets influence the birth and death of stars, determining the fate of entire galaxies. In other words, if we want to understand how the universe works, we need to understand the role black holes play in this billion-year-long dance. At the same time, these extreme objects function as natural laboratories. While here on Earth, we build particle accelerators stretching for kilometers to investigate the laws of physics, the universe has already done the work for us. Black holes show us, in practice, where general relativity and quantum mechanics meet, and where we still don't know how to reconcile them. It's like they're puzzles left on purpose to test how far our curiosity can take us. And despite all the progress, there's still the question that's been echoing since the beginning of our journey. What happens beyond the event horizon? We've managed to detect, classify, and even measure the rotation of black holes. But will we ever discover what the interior of these cosmic abysses is like? Or will this remain the universe's greatest secret? Don't miss out. Subscribe to the channel for more cosmic secrets.